For what value of x do the power series converge? The series at n go from 1 to infinity of negative 1 to the n minus 1, x to the power 2n minus 1 over 2n minus 1. When n equals 1, the term is positive, and we have x to the 2 times 1 is 2, 2 minus 1 is 1, so it is x over 1. When n equals 2, the term is negative, so we have x cubed over 3. 2n minus 1 is the formula for an odd integers. To determine the value of x where the power series converges, we would need to use the ratio test. The limits at n go to infinity of the absolute value of a sub n plus 1 over a sub n, where a sub n plus 1 is 1 more from a sub n. Clearly write out a sub n. A sub n is negative 1 to the n minus 1, x to the 2n minus 1 over 2n minus 1. So that a sub n plus 1 is, we simply rewrite everything and replace n with n plus 1. The power of negative 1 is now n plus 1 minus 1 times x to the 2, open the parentheses, minus 1. Inside this parenthesis is an n plus 1. And similarly, in the denominator, 2 times, open the parentheses, closes, minus 1. And that is n plus 1 inside the parentheses. Note that after we write a sub n, to get a sub n plus 1, we simply replace n with n plus 1. But be careful, we must use the parentheses around n plus 1 if it is an expression. In this case, we're taking the absolute value of the ratio, so there's no need to write the negative 1 to the n minus 1 factor. We still need to write the absolute value because of the variable x. A sub n plus 1 is now x to the 2n plus 2 minus 1 over 2n plus 2 minus 1. Divided by a sub n is the same as multiplying the reciprocal of a sub n. But the reciprocal of a sub n is 2n minus 1 over x to the 2n minus 1. We then need to simplify this expression before we can find the limit. The limits at n go to infinity, the absolute value, x to the 2n minus 1 times x squared times 2n minus 1 in the numerator. Notice that we can write x to the 2n plus 2 minus 1 as x to the 2n minus 1 plus 2, and this is x to the 2n minus 1 times x squared. And the reason why we want to write it in this way, because we have a factor of x to the 2n minus 1 in the denominator, so we will anticipate that we will be able to cancel this out. 2n plus 2 minus 1 is 2n plus 1. And we have a factor x to the 2n minus 1, so it canceled out. We end up with the limit as n goes to infinity of the absolute value of x squared times 2n minus 1 over 2n plus 1. We then factor out x squared and bring it to the front of the limit, so this is x squared. There's no need to use the absolute value around x squared. The limits at n go to infinity of 2n minus 1 over 2n plus 1. We cannot factor any factor with n because this limit depends on n. This limit is 1 because 2n over 2n is 1, so we end up with x squared. X squared is the limit of the expression in the ratio test. For the series to converge, we would need this limit to be less than 1. But if x squared is less than 1, then we need to have negative 1 less than x less than 1. And so for any value between -1 and 1, inside the interval -1 to 1, the series converges. But what happens when x is -1 and when x equals 1? That is when this limit is 1. But the ratio test is inconclusive when the limit is 1, so we will still need to check the endpoints. To check the series at x equals -1, which is the left endpoint, we simply plugged in -1 into x for the given series and go from 1 to infinity, -1 to the n minus 1. X is now -1 to the 2n minus 1 over 2n minus 1. We can rewrite this as n go from 1 to infinity, -1 to the n minus 1 plus 2n minus 1, because -1 is the same base. The denominator is 2n minus 1. This is the series n go from 1 to infinity. The denominator is 2n minus 1, and the numerator is -1 raised to 3n minus 2. This is n equals 1 to infinity, -1 to the 3n over -1 squared, and then the denominator is 2n minus 1. -1 raised to the 3n is simply -1 to the n, because when n equals 1, 3n can be either even or odd. -1 squared in the denominator is now positive, and we have 2n minus 1 in the denominator. This is a convergent alternating series. If we were to perform the alternating series test, we see that 1 over 2n minus 1 is decreasing, and the limits of 1 over 2n minus 1 go to 0. And so we know that this series converges. To check the right endpoint for x equals 1, we plugged in 1 into x, the series at n go from 1 to infinity of -1 to the n minus 1 times 1 to the 2n minus 1 over 2n minus 1. And this is the series n equals 1 to infinity, -1 to the power n minus 1 over 2n minus 1, because 1 raised to any power is itself. This is also an alternating series, and we see that with the same reason, 1 over 2n minus 1 go to 0, and 1 over 2n minus 1 is decreasing, so that this series also converges. And again, this is by the alternating series test. There are two conditions if we want to check this. First, we need to check that the limits at n go to infinity of 1 over 2n minus 1 equals 0, and this satisfies the first condition. The second condition is that the term has to be decreasing. We make f of x equals 1 over 2x minus 1, and we see that the derivative f prime of x is -1 2x minus 1 to the -2 times 2, and so this is always negative, because this is -2 over 2x minus 1 squared in the denominator. Since the derivative is negative, the terms is decreasing because the function is decreasing. We conclude that the given series is convergent for all of the x between the closed interval -1 and +1. This is for all of the x on the closed interval, open bracket, close bracket. This is -1 less than or equal to x less than or equal to 1.